We've been looking at these optimization problems. The critical thing is to figure out what it is you want to optimize and look for constraints in order to write it as a function of one variable. Help to read the problem slowly, draw a picture, introduce variables where you need to. Once you've got the function, then it's the usual critical points and endpoints where you're looking for your max or min. So let's see, we've got this example. The strength S of a rectangular wooden beam is proportional to its width times the square of its depth. So you can just see if you have a beam, imagine this beam running along, right? It's gonna have a particular strength. We could use a particular load on it. But what's going to be important is how wide it is, but also what its depth is. Maybe I'll call that H, just because depth I could use D, but a lot of times we take derivatives, we use that little D to represent a tiny difference, and so better maybe to use H. Let's see, they're telling us that the strength is proportional to, that means it's equal to a constant times its width, which is W, times the square of its depth, which I'm going to represent as H squared. Now the question is, find the dimensions of the strongest beam that can be cut from a 12-inch diameter cylindrical log. Okay, so we are going to have a log here, and we're trying to figure out how to cut that log to get us the strongest possible beam. Let's just look at it from the cross section. So this is a 12-inch diameter log, so it's 12 inches across here. Now I kind of see what's going on. We put a beam in there, right? With the biggest beam, its center should go down the center of the log, and we've got, if we draw a line here, this is a radius, so that's got to be 6 inches. And then we have, this is half of the height, 1/2 H here, and then, oh, maybe, you know what might be easier? Rather than doing it with a small triangle, why don't I make it a little bit bigger? I'll draw a line straight across this beam. I want the biggest possible beam, right? You should get it so that you can go all the way across the beam. And then here is our width, and here is our height, and we can tell from the Pythagorean theorem that the sum of the squares of the two shorter sides should be the square of the hypotenuse. Now in our problem we have an h squared, so we could solve h squared for 12 squared minus w squared. It'd be really easy to replace that h squared, so we end up getting the strength as a constant times the width times 12 squared minus the width squared. Now we have some limits here on the width. The widest that the beam can be would be if it was all the way across the log, which would be 12 inches. Of course, that's going to be a pretty weak beam. And the smallest it could be would be if we put it all into height, right? So we would have a width of 0. So we do have a continuous function on a closed bounded interval, so we can just check critical points and endpoints looking for our maximum value. So let's see. So we're going to take ds dw, the derivative with respect to w, which would be the derivative of the first, times the second, plus the first, times the derivative of the second, and the derivative of 12 squared is 0, so we get times minus 2w. So if I have a k times 12 squared minus kw squared and minus 2kw squared. Oops, 2kw squared. Okay, so altogether I have k times 12 squared minus 3w squared. Looking for critical points, places where the derivative is 0 or undefined. So the derivative is always defined, so let me go ahead and set it equal to 0, look for that kind of critical point. That's going to be 0. Then 12 squared has to equal 3 times w squared. 12 squared is 144, and 3 will go into 144. Let's see, 9 times, or 3 times 16 is 48. Okay, so w squared would have to be 48. So knowing that, then w would be the square root of 48, which would be 4 root 3. So the width would be 4 root 3. If w squared is 48, that also tells us what h squared needs to be, because h squared is 12 squared minus w squared, and 144 minus 48 would be 96. So h squared would be the square root, or sorry, h would be the square root of 96. And let's see, that is 96 is 16 times. Oh no, it's not. 96 is 16 times 6. So this would be 4 root 6 for the height. Okay, if we square those up, do we get 6 times 16 would be 60 plus 36. Yep, I think we're good. Okay, so we've found those dimensions. Oh, I didn't check to see, but we had our endpoints. Obviously, the strength when the width is 0 is going to be 0 times 12 squared, so that's 0. And the strength when the width is 12, 12 squared minus 12 squared would be 0, so we had no strength if we have a beam that's infinitely thin this way or infinitely thin that way. And then we had this one critical point at 4 root 3. And that's going to come out to be a positive value, so we know it's going to be good. We've got k times 4 root 3 times 144 minus 4 root 3 squared is 48. So that's definitely a positive number. This must be our max just by the extreme value theorem. So these are our dimensions. It should be 4 root 3 inches by, and let's see, h we decided would be 4 root 6 inches. Okay, so good. So this h should be square root of 2 times the width. Get the strongest possible beam.